Hello everyone. Today we're going to look at the duality between maximization of the utility and the minimization of expenditure. Okay, we're going to use a typical Cobb-Douglas function. So x1 alpha, x2 alpha, x2 1 minus alpha. Okay, so we're going to maximize the utility subject to the budget constraint. So this is typical. So we form the Lagrange, right? And then we get the first order conditions. So we're taking the derivative of L with respect to x1, x2, and lambda. So if you do combine the first two equations, you will be getting this. Okay, and from there you should be able to find x2 or x1, right? So let's say you choose to solve for x2 and you plug it into the third equation. Okay, so if you do that, you can now solve for x1. So this equation here will now be just a function of x1. So you can solve for x1 as a function of prices and income. Now, after you have x1 as a function of price and income, you can use this one again, right? You can plug it in there and then you'll have this. Now, let's go to the indirect utility function. So what happens if you get the Marshall demand functions, okay, x1 and x2 as a function of price and income, those are Marshall demand functions, and you plug it back into the utility function. So you will have a utility which is a function of prices and income because x1 and x2 are functions of prices and income. So the v is a function of p and m. This is what you call the indirect utility function. Now let's look at the dual problem, right? Expenditure minimization. So we want to minimize the expenditure subject to the constraint that your utility will be at least u bar. Okay, so we form again the Lagrange and we take the first order conditions. Okay, so taking the derivative with respect to x1 and x2, you can notice that those two conditions, those two equations will yield the same as the as the utility maximization problem, right? And then you can again solve for either x1 or x2 in here and plug it back into the third equation here. And so what you have here is utility, the target utility as a function of x1 alone, or x2 alone if you choose to solve for x1 here. So in this case here, I solve for x2 and plug it back in here. So x2 is gone, so u is gonna be a function of x1 alone. And if I solve x1, it will be x1 as a function of utility and the prices. And then there's a special name for that, you call it Hicksian demand function. Okay? And you do the same thing for x2. Either you plug this back in to this one, or you solve for x1 here and then plug it back into equation 3 and then you get x2. Now, same idea. Okay, what will happen if I get the Hicksian demand function and plug it back into the expenditure, right? So I will be getting an E as a function of PU, right? So this means that this is how much you will spend if you want to have a target utility given the prices, okay? So that's EPU. You can definitely simplify this further, right? Tidy it up a little bit. Okay, so this will have a big constant in here. Let's call it K. Now, let's look at Shepard's lemma. So if you take the expenditure as a function of P and U, and you take the derivative of that, partial derivative of that with respect to prices, you should be getting the Hicksian demand. Well, the intuition is really simple, so E is just summation of price and X. So if you take the partial derivative of E with respect to P, then you will have Pi, then you will have Xi, and that works well on how you can remember the Shepard's lemma. Alright, so that concludes the duality between utility maximization and expenditure minimization problem. Okay, thanks.